In this lesson, we're going to talk about tangential speed. And the tangential speed of something is the linear speed of any particular point on something that is rotating. So the unit for tangential speed or linear speed is going to be meters per second. And speed, as we remember, is distance divided by time. So what we're talking about with tangential speed is this vector right here, the speed of this point as this thing is rotating. And the speed of this point right here is going to be larger than the speed of, let's say, if I put an X right there, than the speed of that point. Because this dot goes a further linear distance in the same amount of time. This X goes a shorter distance in the same amount of time. Therefore, the tangential speed depends on how far away we are from the rotational axis. And one equation to find tangential speed is r times omega. The angular speed multiplied by the distance away that that point is from the rotational axis, that'll give you the tangential speed. You might remember that the period is the time in seconds to go around once, and the frequency is the number of go-rounds, or the number of cycles, usually in 1 second. And way back when we were young, we went through an equation that looked like this, that the period and the frequency were inverses of each other. That's going to come into play next. But before we use that, omega, as we know, is angular speed, and angular speed is angular displacement divided by time. Well, if the time is the time to go around once, I'm going to use capital T, which indicates period here, and we go around once, that would be going around 2 pi radians. You can see that omega is 2 pi divided by the period. See, omega is angular displacement divided by time. Well, if the angular displacement is 2 pi radians, then the time is the period that takes. And using that equation in conjunction with the one that's boxed in near the top of the page, we can see that the tangential speed is equal to r times omega. Omega is 2 pi divided by t if we multiply by r. So there is another expression for tangential speed. And we can give one more. Because, as we know from this relation that I'm putting an arrow next to right now, the period and the frequency are inverses of each other. If omega is 2 pi divided by t, isn't it equally true that omega is 2 pi multiplied by f? Therefore, final expression for tangential speed, 2 pi r f. Any of those equations, depending on what we're given, will give us our tangential speed. Similarly, a tangential acceleration is the linear acceleration. In other words, it's going to be in meters per second squared, just like we're used to, of any particular point on our rotating object. Once again, the distance away from the axis is going to make a difference. The tangential acceleration is r times alpha. Alpha is the same for any point on this rotating thing. The alpha of one point is equal to the alpha at any other point, but the tangential acceleration depends on how far away we are. One more thing here. We just wrote down on the previous page for me an equation for tangential speed. And when we first started these kinematics problems, we said that the linear distance, or the arc length, is equal to r times the angular displacement. I'm hoping that you can see a correspondence with these three equations. In short, a tangential quantity, or a linear quantity, if you want to call it that, is equal to r, the distance we are from the rotational axis, multiplied by some angular quantity. That pattern holds for acceleration, velocity, and also for distance. A tangential quantity is equal to how far away we are from the rotational axis multiplied by the corresponding angular quantity. We'll have occasion to use all of these equations as we move forward.